Hello, testing. Thank you very much. I'd like to thank the organizers.
Can we somehow prevent that from happening when we're getting twice everything? I don't know. Well, okay. So I'm going to talk about Serre Duality and Supermanifold Duality. Can you hear me? Okay. And so first a review. What is 1-1 supercurve duality, and what is a 1-1 supercurve to begin with? So the underlying principle is that when you talk about a supercurve, you shouldn't just consider them in isolation. You don't want to just have one supercurve like that. You really want a family of them over a little base here. And the base is important because you want to have odd parameters in the description of your supercurve. So it dawned on me this morning that there are probably not a lot of algebraic geometers in the room. I don't know, but if I talk about schemes and things like that, if you want me to clarify, just let me know, and I'll try to give you a crash course. The important thing is that the base ring, this scheme down here, should have some non-trivial odd directions, and without that, you don't really see all the phenomena. So we'll have, but I'm not going to go hog wild on the base. The base is just going to be a little infinitesimal thing. It's just going to be a point with a little fuzz on it. I'll call it a fat point. So we have a fat point, and our Riemann surface up here with some fuzz around it, and this fuzz is in the form of this coordinate theta here. Let's see, right there, which is an odd variable. So we have one even variable and one odd variable. This is the 1-1 case. We have one even variable and one odd variable. And you can do this in the holomorphic setting or the algebraic setting. The important thing is that dz and d theta are free generators for the cotangent sheaf. That's the key thing. So let's see. Right. So then in 1988, there was a very interesting paper. I call it the A to the 5th paper, for the obvious reasons. A's. So if you have a 1-1 supercurve and you take a Cartier divisor, so what does that mean? It means you have a meromorphic function defined at a point modulo in holomorphic functions. And it's effective and it has degree 1. That means Chern class is 1. The Chern class is a topological thing that doesn't see any of the fuzz, so that's what you know and love about. That's the usual notion of Chern class that you know, and you can use this freedom of the choosing the modding out by holomorphic functions to put your divisor into this particular form, 1 over z minus a minus rho theta, and a and rho are just some new variables that pop up. So basically what happens is that by parameterizing effective Cartier divisors, you get two new variables, a and theta, and they vary according to a different law from the way that z and theta vary, and that set of divisors is again another supercurve. So you start with one supercurve and you get another one for free, and this turns out to be so there's another supercurve that parameterizes effective Cartier divisors of degree 1. And then what happens is that you can do this again, and it's a duality. So you get, if you take the dual of the dual, you get the original supercurve back. And let's just count dimensions. So we have a 1-1 curve. We can take its Cartesian product with this dual thing. That's a 2-2 supermanifold. And this divisor, yes. So the point is that this dual curve parameterizes divisors, and so there's a sort of a tautological divisor on the product, which sort of exhibits this thing as the divisors on that thing. So that's the sort of tautological divisor delta, and it's a codimension 1 thing. So you get a now when you take that delta, you lose the one even coordinate here. So you have 1 even and 2 odd. So 1/2 supercurve, and then there is fuzz. That's the fuzz is the row. This row is odd here. That's the fuzz. And yeah, so that's often called the superdiagonal. And let's see, I don't think I've told you yet how to get the actual dual curve. So now we have a 1-2 thing. And in order to go any further, I have to sort of now in principle you can patch everything together. If you change the coordinates, I've told you how to change the coordinates on the dual thing, on the 1-2 thing. But it's better to give it a more intrinsic definition. So an intrinsic definition of the 1-2 object that I just created so here's our 1-1 object, x, and we're going to have this x tilde. This is a 1-2 thing. And I'm going to tell you intrinsically how to get that 1-2 thing without patching. So what you do is you take the differential forms, the exterior forms, exactly the same way that you would do for an ordinary manifold. And D is an odd derivation, so it reverses the parity, which means that d theta, where theta was an odd variable, d theta is now an even variable, and dz is an odd variable. So now you can do something that makes no sense in the classical it has no classical counterpart. You have a z-graded sheaf of algebras here, and when you have a sheaf of z-graded algebras, you can take the proj of that. And if you do that in the classical case, all the variables that are all the homogeneous coordinates in your proj are nilpotent, and so you can't invert any of them. But now we have one even variable in our proj that we can invert. dz cannot be inverted, but d theta can be inverted, and so we get something. So we're going to regard d theta and dz as homogeneous coordinates on a projective space. Just imagine the usual description of projective space in terms of homogeneous coordinates, and you have one of them happens to be even and the other one happens to be odd. But because dz is nilpotent, you can't invert it. So even though there are two homogeneous coordinates, there's only one chart. The only chart that's available to you is to invert d theta. So you have this thing dz divided by d theta. That's a formal fraction, just as you would do with ordinary projective space. And all right, so now you have coordinates. You have your z and your theta from before, and you have this new guy rho. So this is the 1-2 thing. And what we want to get is a 1-1 thing, and this is the really cool part. So there's good old d, our old friend, the exterior derivative, which goes from omega I d omega I plus 1. It's the same d that you have in ordinary manifolds. And now you can take the direct sum of these over I. And then there's this trick in projective geometry where if you have a graded ring and you shift the degree by 1, and then there's a sort of a sheafification process, you get a line bundle. And so we can think of that line bundle is called O of 1. So O of 1 is associated to shifting the degree. Where is this? Oops. Here we are. It's associated to shifting the degree. So then this d, which is defined from omega I to omega I plus 1, can be interpreted as a derivation with values in this twisted line bundle. Now, when you have a derivation with values in a line bundle, you can still talk about the kernel of it. So basically what you have is a distribution. You don't have a vector field because it's not It's not going from O to O, but that's okay. It doesn't matter. You just locally trivialize that, and then you have a vector field, and that vector field is well defined up to scaling. That's what we call a distribution, and it's got rank 0, 1 because D is odd, and so you can take the leaf space of that, and that kills off one more. That kills off one of the odd directions here. So now you have. Now you can come down this way, and this is the kernel of this D thing. None of this would make any sense classically because it would just be the empty set. But that's the leaf space of this distribution is the dual curve. So that's an intrinsic way of describing the dual curve. And as I indicated before, you could have done this all by patching. So what you could have done was just tell me how to take coordinates z and theta on x and get coordinates z hat and theta hat on the dual curve. And what you have to work out is that D is supposed to be 0. So let's take a look at this right here. Now when you do D on a fraction, it's just the quotient rule. So those guys are closed. So you have dz, there's a little exercise, dz minus d theta over d theta dz. That's D of that is 0. And this one obviously also has D is equal to 0. So there you go. Now, what does this all say in the familiar world where there are no odd parameters in the base? If the base scheme is just even, maybe just the complex numbers, 1 point, or there are no other odd variables, then what happens? You have a 1-1 thing. So you have 1-1, and there's no odd parameters. So you have the structure sheaf of the reduced space plus the odd part, I'll call that L, and that's a line bundle over the reduced thing. So in the 1-1 case, when there are no odd parameters, you simply have a line bundle. That's all it is. You just have a Riemann surface with a line bundle. Or maybe a slightly deformed family of Riemann surfaces with a family of line bundles. So it's just a line bundle. So what is this duality in that case? That's a perfectly legitimate case to consider. So let's just look at the formulas here. We have another coordinate system, W eta, and we just follow the rules for making eta hat and W hat the same way we made Z hat and theta hat, and it works out to this thing here. And then here's the magic of nilpotence here. So this theta hat, what you do here is you factor out G and you write this reciprocal as you invert it by the Taylor series, by the power series, geometric series, and the theta hat will kill that theta hat, so that this G prime thing just disappears, and eta hat is just F prime theta hat over G. And W hat works out to F of Z hat. So basically, nothing's happening in the even part, and the odd part, you might recognize this, G was the transition function from my original line bundle. It's now in the denominator. And F prime, well, that signals that you have the canonical bundle, the cotangent bundle. So this is the transformation law for the Serre dual line bundle. So all this stuff just breaks down to the Serre dual in the case where there's no odd parameters. Any questions so far? Let's see. Okay, so we have this Serre duality for line bundles, which becomes a much bigger duality for 1-1 curves over an arbitrary base scheme. We can allow as much nilpotence as we want and odd stuff as we want in the base. We can deform to our heart's content. And then there's good old-fashioned Serre duality that we have for a long time now, which works in not just the 1-1 case, but in any dimensions. We have Serre duality in all dimensions, if the conditions are right. So the question is, why is it, or do we have to live with the fact that in the 1-1 case, you have arbitrary base schemes, and in the 1n or mn case, you have just, as far as we know, no way to tie these two things together. So the question is, can we find a natural category of supermanifolds which can accommodate both the Serre duality, which is defined over the complex numbers, or even base schemes together with the this much more general duality in the 1-1 case. And well, people, I mean, this duality was, as I said, pointed out in 1988, so people had a long time to think about it. And in the early first couple of years after that paper appeared, there were various arguments given as to why this couldn't work. And I took a look at those arguments, and I didn't believe any of them. So being the stubborn person that I am, I decided to see what I could do. So this product construction that we just made, you can always do that. You can take the this graded sheaf here, and you'll have a bunch of odd variables that become even variables when you apply D, and so you can do all that. But of course, what you get is very big, because as soon as you have several odd variables, you get your projective space is no longer affine. So you have an honest to goodness, you've actually changed the space. I should mention that none of these operations change the underlying manifold. We're just adding some odd coordinates. So so you get something of dimension n plus m minus 1, n plus m minus 1, which fortunately when n and m are both 1, it works. That's the dual curve in that case, but it doesn't work in general. Effective divisors, that was the first thing that people tried, but there are too many of those. Once you have more than one odd variable, there are too many parameters, and you get a space, some kind of something like a Hilbert scheme, but a little not quite as complicated, but that's not going to be what you want. So let's just take a look at the Serre dual and see what we've got. And I should say I don't have all the answers here. Don't even have any answers here. And I'm more than happy to talk to anyone about this that wants to explore this further with me. But I'm going to bring you up to the point where I think I'll convince you that something's going to work, and then we'll go from there. So I'm going to call the Serre dual E dagger. That's the dual. So now I have a vector bundle E. I should have said E is a rank 2 or higher vector bundle, locally free sheaf, if you like that kind of language, on our Riemann surface. And the Serre dual is the ordinary dual. This stars the ordinary dual times kappa, which is called the canonical bundle sometimes. It's also omega 1. It's the same thing as we had before. And it's the line bundle which is locally generated by dz. Now, here's what happens in the 0n case. You have the usual, this is sometimes called the Hodge star, but it's also, if you think about supermanifold, it's really Serre duality in the 0n case. So if you're familiar with this formula, you take the ith exterior power of the dual vector bundle, then it is naturally isomorphic to the n minus I power of the original bundle times the top exterior power of the dual bundle. This is just basically contraction. The way this works is you take a top form in the dual and you contract it with these n minus I things, and you get an I thing in the dual. So that's what we're working with. So when I plug that in here, when I put in the canonical, the kappa in here, that throws in a bunch of powers of kappa, and I get, for the ith one, I get the ith power of kappa. But this isomorphism is backwards, and that's going to be critical for us. So the top becomes the bottom, and the bottom becomes the top. So that's backwards, and I'll say more about that later. So now what we have to do is look for something that sort of behaves in this way. And this turns out to be a very good candidate. We're going to take the nth symmetric power of the cotangent sheaf. So this is going to be, and pi is parity reversal. So let me illustrate that a little bit. So in the 1-1 case, you have dz and d theta. Now you notice that I have sim here. This is not wedge, this is sim. So in the sim world, this would be even, and this would be odd. So in the 1-1 case, I wanted to divide by d theta, so I had to make it even. So that would be, so what I really did when I made that product construction was I took the cotangent sheaf and I reversed the parity of it. So this is pi, which is the functor that takes a graded module and simply interchanges the meanings of the 0 and 1 pieces. So the 0 piece becomes the 1 piece, and the 1 piece becomes the 0 piece. So we'll do this in such a way that when we get to this, so now we're going to take the n symmetric power, where n is the odd dimension. So we're looking at the 1n case. And the beautiful thing is that you get, once you get up to n or higher, but n is a good place to stop. Once you get a vector bundle over your supermanifold whose rank is precisely the rank of the dimension of the Grassmann algebra, and in fact it looks like the Grassmann algebra. And we've reversed the parity if necessary. So if n is odd, we reverse the parity, otherwise not, so that we have this even gadget right here at the end. And we want to invert that. But remember that d theta is odd. So you object. Isn't that nilpotent, you ask? Okay. Yes. But only if we remember where it came from. So, I was teaching linear algebra. I'm teaching linear algebra this semester, and I did it with wedge products and Grassmann algebra and stuff, and I got to the point where I had this thing, and I said, now you just sort of cancel that. You get that factor, and then there's the topic series power, and you just cancel it. But how can you cancel it? It's nilpotent. You can't divide by it. But you forget that's where you forget that it came. You forget. The basic idea is that you forget that this sim n of t star is sim n of anything, and you just call it something new, f, and you forget its origins. And now we can proj sim f perfectly well. And we'll ignore the fact that f was sim n of anything. So now we have something that could possibly be the basis for constructing the dual. But we remember the structure group that gave rise to this object. So when we change coordinates, we're not going to just change coordinates willy-nilly on f. We're going to change coordinates only using the change of variables in the base manifold. So that gives us. So we'll have a set of coordinates given a chart. Given a chart with coordinates z, theta 1 through theta n, we'll get coordinates on this f thing, and this mu index here stands for any subset of the numbers from 1 to n. So these are basically Grassmann variables. And so let me illustrate with n equals 2. So we'll have dz squared, dz d theta 1, dz d theta 2, and d theta 1 d theta 2. But I want to forget that these are products of one forms, or sections of the cotangent sheaf, and I just want to treat them as new variables in their own right. So in order to not get confused, I'm just going to call this one A empty set, A1, A2, and A1, 2. And I've reversed the parity if necessary. Now, when n equals 2, I don't have to reverse the parity. So this is even, and this is even. And these are odd. And I just take a look at how those four generators for my vector bundle transform when I make a change of coordinates, and I'll get something. Now, the whole idea in, as I pointed out, when you do the Serre dual and you use that Hodge star, everything comes out backwards. So you basically want to take the top form and treat it as if it's the bottom, and the bottom becomes the top. So the idea is to read the exterior algebra backwards, which is basically the Hodge star, and hope to find another supercurve such that when you start with that other supercurve, you arrive at this reversed thing. That's basically the plan. And later on, let's see, I don't know what time is it. How much time do I have? I have half an hour? 5 minutes, okay. So, yeah, so toward the end, I'll explain a little bit more about the sort of the grand vision of what this is supposed to accomplish for us. But let's just keep doing the nuts and bolts here for a minute. So now, having ignored the fact that f was sim n of anything, we have to now remember that. But we're going to apply that to this purported dual object, which is yet to be produced. So we're going to. So the idea is now. Oops! There's a topological obstruction. Ooh, I have a problem here. Okay, hang on. For this plan to succeed, this z hat is going to be our even coordinate on the dual curve, and this guy over here was dz squared. So this purported dual thing is going to have the property that when I parity reverse this guy, which I don't have to do because n is even here, I get the square of something. Now let's see what happens when we change coordinates. So take another coordinate system, w eta, let's say, and let's look at, so I should adorn this with the name of the coordinate system, so z theta up here. I abbreviated that to sigma. So now we have another coordinate system, tau, which is w's and etas, and when we transform, make a change of coordinates, we get the determinant of the derivative of the odd variables with respect to the odd variables times the generator in the other coordinate system plus some other stuff. Now, this other stuff is going to be in the ideal generated by odd functions. So it's going to be nilpotent, and we won't have to worry very much about it. So in order to reconcile these two things, it would appear that we would have to, when we make a change of variables, we would have to extract an nth root of this determinant. Now, you could do that by making an étale cover of your curve, but that would change the curve. And the whole idea here is we don't change the curve, we just change this sort of fuzz part. So that looks like it might be a problem, but it's not, because we're doing a proj. Now, when you do a proj, you know that the classical way of thinking about projective space is that you have homogeneous coordinates, and you declare two to be equivalent if one's a multiple of the other. And what that turns out to mean in the vector bundle world is that if you tensor a vector bundle with a line bundle, that's just like rescaling the homogeneous coordinates. It doesn't change at all. So that's what makes it a proj. The vector bundle is unchanged. If we tensor with the line bundle, that's what makes it a proj. So now, can we find a line bundle on our curve that's glued together in such a way that, are there line bundles such that if we tensor, so we just sort of tensor in some line bundle here, that we can extract the root that we want to extract. So this becomes a question of what kind of line bundles are there on a supercurve? And which transformation should we look for? Well, we're trying to make an involution. We want this duality to be a duality, so there's a natural choice, it turns out. So if we had a line bundle that had local trivializations like this, that glue together in this particular way, we have the n minus first power of the determinant on top and the nth power of the derivative of the even variables on the bottom, modulo this ideal that we're not going to worry about, then you could just redefine, so I'll just redefine these things to be with that line bundle in them, and then when I make that transformation, voila, I get an nth power here, and it's the nth power of this thing. So now the question is, are there line bundles that do that? Yes, such line bundles exist. And the reason that they exist is that we're on a curve, and if you work through the process of trying to construct such a line bundle, then you find that the obstruction is an H2 of something. And it's an H2 of something that's not immediately clear that the H2 would vanish. But if you think about it for a few minutes, you realize that it's filtered. This is sort of a standard filtration argument. The sheaf is, well, basically what happens is you're going to take your structure sheaf and mod out by the ideal, and you have a line bundle. Now there you have the line bundles that you want. So if you mod out by the ideal generated by the odd part, you have the line bundles that you want. So you have a line bundle that transforms this way, and a line bundle that transforms that way, modulo the ideal generated by the odd part. So that means that you can locally create the line bundle that you want, and the obstruction will be an H2 of something that is 1 when you mod out by the odd part. Then you can filter that and use the fact that you're on a curve and these are coherent, O-coherent sheaves, and you use descending induction, so the line bundle that you want is actually there. So now the question is there a dual curve such that when I take my starting point, which is sim n, and I tensor in with this line bundle, that I get the n symmetric power of some other curve. And I don't
Start with x.
start with x.
Start with x.
Take this n.
Find the line bundle that makes that.
Yes. So
And the x hat is.
Yeah. So the picture should be. Picture should be that you have a 1n curve here, starting point, and we're going to construct this sim n t star x, so that's going to be proj of sim n of t star x. Let's do n equals 2, because I can't think any higher than that. So just 2. If we can do 2, then we've got something. So this is a sim 2 of t star x has rank 2, 2. So then we make that vector bundle that has rank 3, 4, I guess. And then there's supposed to be another guy over here, also 1, 2-dimensional. And well, when I proj this thing, the line bundle doesn't change. So I get the same space up here. And I should have, like, this is basically the picture. And I have yet to see why that shouldn't work, but I haven't yet to finish it. So that's a proposal or a question which I put to you and anybody else that wants to think about it. Now I want to also talk a little bit about. I think that's maybe it for my slide presentation. So the rest of this is going to be at the board here, and you just tell me when to stop, and I'll stop. So why would you want to do this anyway? What's the big idea? Well, there's this thing called the functor of points. And this goes back to the beginning of the foundations of this subject many years ago. And so what you do is you take your supermanifold, and you take well, the easiest thing to do is to take a fairly small super scheme. Take a spec of T, where T is some finite dimensional finite dimensional superalgebra, commutative superalgebra. And you look at maps from your little baby super scheme to your big interesting super scheme. And this is now a set, but it's a functor of t, and you can capture x from this functor. So this is the functor. This functor of points enables you to think of this more abstract structure sheaf as something very concrete, just a set of an ordinary set with maybe some extra structure on it. Now it turns out that if you have x, I said at the beginning of the talk that you have to allow odd variables in the base because you don't see all the phenomena otherwise. So, for example, if you take x over spec s, and you ask yourself, if I know the s points, do I know x? The answer is no, because you're going to lose the odd information that's up here in the structure sheet. But it turns out that if this is a 1n dimensional thing, or mn dimensional, doesn't matter. If you have n odd variables, then it suffices. So the proposition, the spec of s of alpha 1 through alpha n, these are odd variables, points, determine x. So s might be too small to capture all the phenomena that you want to capture, but if you put in as many odd parameters as you have odd coordinates, then that'll do the job. So I just take my whatever base scheme I started with, which I'm just thinking of this as a fat point, and I make another fat point by just adjoining n anti-commuting, right? That supercommute with s and supercommute with each other. And so now the key thing about this, here's the big difference between ordinary geometry and supergeometry. This construction that I'm talking about, this Hom dot x construction, this is classical. So for example, if you take so-called dual numbers, so let's say C of E, normally it's usually called epsilon, but I'm trying to reserve Greek letters for odd things. So I'll call it E modulo E squared. So this is just C plus EC. And you look at Hom, it's for an ordinary manifold now, nothing super here. You just look at Hom from this thing to your manifold. I call it M for manifold. It's a regular C infinity manifold, nothing fancy here. Maybe this is R. We can even do it over the reals. Then this is a familiar object. What object is this? It's the tangent bundle, right? This is the tangent bundle manifold. Because you're telling me, you're giving me a point, you're giving me a point and a little nearby point. So E squared is 0, so you have a point and a nearby point. So that's the tangent bundle. But now, the big difference, and this is really, I think perhaps the most important difference between ordinary geometry and supergeometry is that you can do the same thing with theta, or alpha's odd. And let's compare these guys. See, here the thing is, if you want an even variable to be nilpotent, you have to tell it to be nilpotent. You have to say, you're nilpotent. I'm sorry. That's just life. It doesn't want to be nilpotent. E doesn't want to be nilpotent. You have to tell it to be nilpotent. But you don't have to tell alpha to be nilpotent. Alpha's odd. It's automatically nilpotent. You don't have to force it. It's just naturally nilpotent. And what does that mean? That means this is a group. If I do spec of this, this is a big difference. This is a group. And this is not a group. So the big picture is that you take your 1n curve and you look at the points with that. You look at the maps from this group. So I'm going to really emphasize that it's a group. So this is the additive group of dimension 0n. That's spec of, well, this is S points. You look at the maps from this group, to your supermanifold, and you can ask if this is representable, and it is representable. So that means that it is the set of ordinary S points into some other supermanifold. And the example here is, again, if you go back to the commuting case and you just take this to be the dual numbers, this would be the tangent bundle. So this is something like the tangent bundle. But it's nonlinear and it's odd because you have this n, which is bigger than 1. If n were 1, this would be called the odd tangent bundle. If n is 1. So now, this is just a set. We've taken the functors out of it. There's no place to put anything in there. So this is just a set. And because this group is a group, there's a map from a point. That's the identity element. Just the identity element of the group. Actually, called 0, better name for it. So that means that you can take one of these homomorphisms and evaluate it at this point, and that gives you a map to X. So again, in the case of the dual numbers, this is just the statement that the tangent bundle is a bundle over the base manifold. But there's another map, which is, so you can now take the group here, take the Cartesian product, and you can take that same map where you simply take a point, take the identity element, and so there's this map, but I'll call this pi 1, and I'll call this, yes, pi 1. But there's another map which says, look here, a point of this thing is a homomorphism from that thing to that thing. So I can take a point here and a thing here, and I can evaluate. So that's another map. This is a map that says take a homomorphism. This is sort of the dumb map. Take a homomorphism and take a point and send the ordered pair G phi to phi of G, which is plugging in the point into the homomorphism. So there are these two maps. Now you can do this with the dual numbers in the classical case, and this is just the this is in the classical case. This is just F versus F plus DF. These are the two maps. So this is some kind of nonlinear, odd analog of D. Now, one possible take on this duality picture would be that the dual would interchange these two things. So another conjecture is that, so this is pi 2, is that there's the same thing. The conjecture would be that this is also, so as I said, this is Hom G A N to X. The conjecture would be that this is also Hom from GA 0n to this other thing, and these two things get switched. Now, so just to close, I said that there was this representable functor. This thing was represented by some y. Now, when you take an exterior algebra, there's this beautiful fact about exterior algebras that Hom, let's say exterior algebra over C of a vector space into C, is naturally isomorphic to, well, almost naturally isomorphic to the original. And what you need to do is, it's what I wrote down before, using the Hodge star. So the idea is that you simply take a dualizing element, it's a Gorenstein condition, I think. You take a basis, and you do what I said to do before. Given a basis, you take omega goes to, well, let's see. So this guy goes to 1. And then you take omega wedge, they'll call this guy capital omega. And it's the Hodge star. Some number. It's the determinant. So now if you take, so you can read the exterior algebra backwards, upside down, or backwards, whatever you want to call it. And the question is, if you take the functor, so this is really what I'd like to know. If I take the functor in the category of algebras, now the category of algebras is the opposite category from the category of schemes, affine schemes. So what I would do here is I would take an algebra A, so I would assume let X be the spectrum of some A. So I would look at maps from A to S of the alphas. Now I can forget that that's an algebra map and just think of it as a module map, S modules. This is the forgetful functor. Forget. There's a guy staring at me back here. It was a mural. It's frightening. Then I can do this Hodge star. In S modules, not an algebra anymore. It's not an algebra. The Hodge star is not an algebra homomorphism. It's just a linear map. So I'm in S modules. Then the conjecture would be, I think this is the ultimate my most refined version of the conjecture would be that this would be Hom in algebras of a dual. So that by reading the exterior algebra upside down, which takes you out of the world of algebra homomorphisms, you get back into the world of algebra homomorphisms by replacing A with its alleged dual. That's enough.
And is it possible?
I don't know. I promised you more questions and answers.
But again, how
There you go. Okay, that's all I have to say. Yeah.
Reversal
Mhm.
and then you have this even, start with something even, and end with something even.
Mhm.
Right? And then you parry reverse, but then the functor of points knows all about it, which is right?
Yes, but you have to forget that there's a brutal process of forgetting where this rank 2 in the n equals 2 case, the rank 2 or 2 to the n minus 1 / 2 to the n minus 1 bundle comes from. You take this.
You're trying to forget that, but then the functor of points know.
yeah.
Yes, exactly. So that's right. So you have to get back, but you're going to apply the functor of points to a different curve. That's the idea. That you do this sort of. Oh, another way of thinking about this is that the Serre dual is basically distributions. So you can take. So here's my little lecture on the Berezinian. So the Berezinian basically looks like this. You take n forms. Let's see, this is in the mn case. So mn dimensional supermanifold. You take the m forms and you tensor with the differential operators. And there's a complex. This was actually Penkoff did this. You can do this. And put a dot here. So if you have a differential, so think of this as differential operators with values in forms. And put an I here. And there's a natural sort of de Rham complex associated with this. You can take your operator and compose it with D. So you have like omega tensor L. So omega is an I form and L is a differential operator. And you can take a function. You can apply the operator to the function. You have one form here, and then you can take D of that. So that's going to take you to I plus 1 like this. And Penkoff observed that, so this is a complex. It's a complex of right D modules, and in particular of O modules. And Penkoff observed that, that the cohomology of this complex is 0 most of the time, is non-zero in 1 degree only. And that is that it's M, namely M. And the thing that survives at level M is dz1 through dzm tensor d by d theta 1 through d by d theta n. This is M, this is N. That survives. So if you compose that with D, you will get 0, because when you put a function here, it's got a bunch of thetas in it, but then you kill all those thetas, you differentiate them all away. That was basically the Hodge star. And then you have just a function of z, and then you're at the top of that, so d of that is 0, and it's not d of, it's not a co-boundary.
This is an example of how you go from the top to the bottom.
Yes, exactly. Right, that's right. So in degree, it's non-zero in one degree only, and it's rank 1 in that 1 degree, and that object is the Berezinian. So this is a representative of the Berezinian, modulo things that are decomposed, that's a bad pun, but decomposed with something. And so the Serre duality works like this. Well, there are two Serre duals. This is another part of the puzzle. You can take the Serre dual of a vector bundle and then take its exterior algebra. You can also take the Serre dual of the structure sheaf. This is the structure sheaf of your supermanifold. You can tensor this with the Berezinian. These are different. This is the one that I'm focusing on today. Well, in rank 1, they're the same, but they're different in general. And this one, the way this works is you take this guy, and you divide by, you have some point somewhere. So what you have to do is actually take the diagonal. So I'll take z1 minus w1, zn minus wn. And then you put your function here. You differentiate out all the other variables, and then you take the residue. That's Serre duality in supermanifold language. So that's why I think these three pictures are tied together, because this is all lurking in the background. And well, as I said, there were a number of objections raised in the early days as to why this wouldn't work, but I haven't really found them to be insurmountable at all. So I think this will work. I hope.
Can you do it for different even dimensions? So it seems to be work because
of the one.
dimension is
One. That's a good question. I don't have the answer to that. But I will make one more comment along those lines, which is that if you have...
Is it true that the reason why it is working in this dimension is
in 1-1. It's only... the problem's not solved in 1-2. So, okay. But...
Well, whatever. The reason
that it's looking
why it works
looking promising, let's say.
is because the reason why it is going to work.
Okay, there you go.
Is because when you take the functor of points, you don't really change that. You're not changing you're looking at maps from the underlying algebra into the complex numbers. And so you're not changing.
I think that with bringing this Penkoff picture in, you can do the MN case. I'm not too worried about increasing the even dimension. I think that's manageable. But I do want to make one comment about the 1-1 case. So in the 1-1 case, you start with just a line bundle. And you make a supermanifold where this is the even part and this is the odd part. Now, if you wanted to deform this, the first thing you would try would be to deform it just using the tangent space to the moduli space, which would mean that you would look at maps C of E mod E squared or C of theta, one or the other. And so you end up looking at derivations. So we know that to deform a complex manifold, you want to look at H1 with coefficients in the derivation. So let's look at the derivations. The derivations of this thing. Well, one thing you can do is just differentiate this guy. That would be theta d by d theta. I'm going to do the even derivations first, then I'll do the odd ones. So these are the even derivations. There's theta d by d theta. And that's just O. And then there's, and then just doing the even ones first. The quotient is going to be L. It's going to be kappa inverse. This is basically d by dz. So d by dz doesn't naturally act on here, but there's an extension so that if you mod out by O, then you get a well-defined vector field. In order for this to split, the splitting of this would be a connection. I'm not assuming that L has a connection, so that's the picture in the even case. And in the odd case, the odd derivations, which you have to allow because you're going to have odd parameters that will turn these into even things, but I'm just using this thing now over C. You have the dual, that's just d by d theta. And then you have the line bundle tensored with kappa inverse. That's theta d by dz. So this is the picture. And now this functor is supposed to take this thing to the Serre dual. So if I put in the Serre dual, well, notice that these two things don't have anything to do with the line bundle. So this is invariant under Serre duality. But this one's interesting. So now I'm going to replace L by L inverse kappa. So I'm going to dualize that. So I'm going to get kappa inverse L. Of the dual. And over here, I'm going to replace L with L inverse kappa, and that's kill the kappa, and I get L dual. So it's got the same ingredients, except it's the wrong X'd. This one is X'd of that, and this one's X'd of that. Now they're not the same. But somehow they get mapped to one another under this duality. And this is not new. I mean, this is the 1-1 case. So I don't even think this is completely understood in the 1-1 case, exactly what is going on here. Now, you have to take cohomology of this thing, and you'll have some H. You're going to look at H1 of this guy, and it's going to be sandwiched in between these H1s, and somehow the extension data disappears. Or the Serre duality, the supercurve duality knows how to pick some sort of how to kill the extension class. It's not clear how that works. I mean, one could compute it. One hasn't computed it, but one could compute it.